So we're going to continue our discussion of logistic regression today. And just like last day when we were talking about modeling the probability distributions of our different classes, we're still going to continue with the assumption that we're doing a binary classification problem, or in other words, that we have two classes. Okay, so we'll continue to assume that our data lies in two classes, C1 and C2. Okay, and so remember K was the number of classes we have, so K is going to be 2 in this case. And ultimately we'd like to model the conditional probability, the probability that so if we get a vector x or we get a data point x, we'd like to be able to understand what's the probability that our data point lives in class C1, assuming that we've sampled the point x. Okay, and so what we're going to do is we're going to look at this from a sort of a Bayes rule point of view. So by Bayes rule, we have the following. The conditional probability of C1 given x is equal to the conditional probability of x given C1 times the probability of class C1 all over the probability of x. And so just like last day, we can kind of assume that we have some idea of what the prior distribution of our two classes are. So we can sort of estimate this if we want. This is the likelihood function that we kind of dealt with last day. But we're not going to view it like we did last time. We're not going to do a maximum likelihood estimate. Instead, what we're going to do is we're going to expand the denominator out. So up in the numerator, we still have the following. And in the denominator, we can split this up as the following. In the denominator. Okay? And now what we'll do is we're going to take both the numerator and the denominator, and we're going to divide both of them by what's in the numerator. So we're going to take the numerator, divide it by this, and we're going to take the denominator and divide it by this. So of course, when we do that in the numerator, we're dividing the numerator by itself, so we just get 1. Notice the first term in the denominator is exactly this thing here, so we're dividing that term by itself, and we get 1. And then the second term in the denominator is, of course, the probability of x given C2 times the probability of class C2 all over the thing that we're dividing by. Okay? And, okay, so it doesn't seem immediately obvious why we did that, but we're going to do one other thing that is not sort of immediately obvious why we're doing this, but bear with me for a minute. We're going to take that remaining piece here. We are going to take the logarithm of it and then take the exponentiation of it. So we're going to take exp times the logarithm, okay? And we're essentially going to put this thing inside this logarithm. And since we're taking a logarithm but then we're exponentiating, these two things are going to cancel. But we actually want to put a negative sign here. Okay, and so because we want this negative sign here, when we take this thing and put it in, we've actually got to flip the numerator and denominator. So this gives me the probability of x given C1 times the probability of class C1 over the probability of x given C2 times the probability of class C2. Okay, so notice the negative here, tells me that if I want to bring the negative inside here, I can do that, but then I have to sort of switch the order of the numerator and denominator. and then the exponentiation and logarithms would cancel, and I would just be left with exactly what I have here. Okay. So I'm actually going to give this curious looking function a name. I'm going to call it sigma. And so what we're looking at is sigma of log probability of x given C1 times the probability of C1 over these probabilities here. Okay. Where I'm essentially grouping this 1 over 1 plus e to the negative. So I should sort of say what this sigma is, where sigma is going to be a function from the reals to the reals, is called the logistic sigmoid function, and it's defined by sigma of z is equal to 1 over 1 plus e to the negative z. Okay? So if you look, notice that's exactly what we have here. We have 1 over 1 plus e to the power of something. It just so happens that, or e to the power of negative something. So it just so happens that the thing that we've plugged in here is this logarithm here. Okay? So this expression here is just sigma of log of this. Or, yeah, is sigma of log of this thing here. Okay? So notice all that we've done is we've taken our conditional probability, which is the thing we really want to measure. This is the thing we really want to model. We've expanded it out using Bayes' theorem. And then we took the denominator and we split it up into sort of this like marginalized form. Okay. Then once we did that, we divided the numerator and denominator by the numerator, which gave us 1 over 1 plus this thing here. And then we sort of added the exponentiation and the logarithm here in such a way that they just cancel each other out. But when we've done that, then we sort of, when we define this sigmoid function here, this is exactly what we're left with. We're left with 1 over 1 plus exponentiation of negative log of this piece. So that's just sigma of log of that. Okay. So yeah, maybe pause to sort of make sure you're good with the algebra. Now it again might still sort of be mysterious why we're doing this, but by sort of writing down our conditional probability in this form, it's going to allow us to sort of simplify the situation quite a lot, and it'll allow us to model the situation a lot better. Okay, but let's just talk for a minute about what this sigmoid function is here. Okay, if you were to graph it, if you were to graph this sigmoid function, well, you would notice that the function is always positive. Okay, and because of this negative exponent here, as z goes to negative infinity, this exponent would be going to positive infinity. Therefore, this denominator would be going to infinity, and the whole thing would be going to 0. Okay, so as you go to negative infinity, the function goes to 0. Okay, and you have an asymptote at 0. As you go to positive infinity, this exponent goes to negative infinity, which means this thing goes to 0, and therefore the whole thing goes to 1. So you've got this asymptote as you go to positive infinity at positive 1, and your function sort of looks like this in between. Okay, actually it's a really poor drawing of it. I'm going to draw it again in one fell swoop. It's going to look like this. And it kind of has this S shape here. Okay, so that's kind of why we call it a sigmoid function. The sigmoid comes from sort of the S shape. And I realize it's a little unfortunate that we use sigma to denote the sigmoid function because we use sigma in other places, like with standard deviation and stuff, but it's just sort of the standard notation, and so we're not going to change. Yeah, I mean, that's just sort of what people standardly use. So, okay. So, introducing one more little piece of notation, thus, if we let alpha of x equal this logarithm of this quotient, okay, then we can model so if we do that, we can model this conditional probability that we really want. We can just think of it as being equal to sigma of alpha x. Okay? And so, I mean, it's not really clear what we've gained here, all right? Because if, sure, we've sort of made everything look a lot nicer, but alpha of x is really like this logarithm of a quotient of conditional probabilities, which doesn't seem like it's very nice at all. And then sigma is this sort of, somewhat complicated function as well. So, I mean, it feels like we've just sort of done some notational tricks to sort of hide the complexity there. And so it's not immediately clear what we've gained. However, if we make a few simplifying assumptions on our probability distributions, then it will turn out that this expression here will simplify quite nicely. Okay, and so let's just say what those assumptions are going to be. So these are actually the same assumptions that we made last time. So we'll make some simplifying assumptions. Okay, so we're going to assume that C1 and C2 are normally distributed. Random variables with mean u1 and u2 respectively. And we're going to assume that they again have a common covariance matrix sigma. Okay, so these are exactly the same assumptions that we made when we came up with sort of the maximum likelihood estimate. And so now what we're going to do is we're going to use these assumptions to sort of find a nice simplified form for alpha of x. Okay. Whoops. So alpha of x, by definition, is this logarithm that we've written down, which seems super weird, seems mysterious. This logarithm of this quotient. Okay, and if we write out what each of these is, remember we're going to sort of assume that this prior probability is so the probability of being in class 1 is Q, so that term is Q, and then this conditional probability is given by the normal distribution with mean mu1 and covariance matrix sigma. Okay, and then on the bottom, if the probability of being in class 1 is q, then the probability of being in class 2 is going to be 1 minus q. So we get a 1 minus q on the bottom times, again, the normal distribution with mean mu2 and covariance matrix sigma. Okay? Now if we split this up, this logarithm can be split up into something a little bit nicer. So this will be the logarithm. If I want to split up this product, this is q over, 1 minus q plus the logarithm of the normal distribution minus the logarithm of this normal distribution okay. And now when we actually write everything out, when I write out this distribution here, which we've done kind of a million times, I'm going to get this term here times e to the negative 1/2 x minus u1 sigma inverse and then minus the same thing. Okay, so it's exactly the same thing, except now instead of up here we have instead of mu1 we're going to have mu2, but I'm just going to save myself the trouble of writing that. But notice what's going to happen is when I can split up this product in the logarithm, and I can split up the same product over here, this corresponding term here is going to cancel with the term there. So what I'm going to be left with is log of q over 1 minus q plus, and then when I do that, I'm just left with this exponential inside the logarithm, and same thing over here, but the exponential and the logarithm are going to cancel. So I'm going to be left with minus, after the log and the exponential cancel, I'm going to be left with minus 1/2 x minus mu1 transpose sigma inverse x minus mu2 plus 1/2, oops, that's not an x minus mu2, that's x minus mu1 still. Okay, and if I split this up, essentially what's going to happen, I don't want to write everything out probably, but what's going to happen is for each of these terms, I'm going to sort of like FOIL everything through, okay? And when I regroup, I can FOIL everything through and I can regroup it as follows. So I'm going to get log of q over 1 minus q, and then plus 1/2, let's see, mu1 minus mu2 transpose times x, then plus 1/2 x transpose sigma inverse mu1 minus mu2, okay, then minus 1/2 mu1 mu1 plus 1/2 mu2 mu2. Okay, so what's happened here is essentially what's going to happen is I'm going to kind of FOIL all these things out, right? And over here, I'm going to get a term that involves x sigma inverse and x with a negative 1/2 in front of it, whereas over here I'm going to get a term that has x sigma inverse, and x with a positive 1/2. So that sort of x squared term over here is going to cancel with the corresponding x squared term over here, and I'm not going to get an x squared term. That x squared term is going to cancel. I am, however, going to be left with sort of like two terms that just involve x, right? This term and this term, and then I'm going to have sort of constant terms like this, okay? But notice, because sigma is a covariance matrix, so sigma is symmetric, sigma inverse is also going to be symmetric. And so I can actually just take the transpose of this whole thing. Since this whole thing is just a real number, I can take the transpose, and everything sort of switches orders. And it turns out that this thing here is exactly the same as this thing here, okay? Because you can take the transpose of it and nothing changes. And they're just real numbers, so you can take the transpose and since it's just a real number, taking the transpose doesn't change anything. So if you take the transpose, it's just a real number, nothing changes. But if you sort of bring the transpose in and rewrite everything, you're going to see that the transpose of this term, which is just equal to itself, looks exactly like this term here. And so therefore this term and this term are the same. And so therefore we get a term that looks like this. If this description is really confusing, it's written out, I think, fairly carefully in the notes. So if you want to sort of follow the algebra a little bit more closely in the notes, you can. Okay, and so the point is now, what I'm going to do is I'm going to group this term together with this term, and I'm going to call that W1. So let me actually just rearrange this because I can. I'm going to bring that over here. I'm going to bring this over here. Okay. And I'm going to call this, let's change colors here. I'm going to call this sort of like this term W0. And as ugly as this term is, notice everything in this term here is actually just a scalar. Okay? So this term looks really nasty, but everything's just a scalar. So I'm just going to group that all together and call that W0. It's a scalar. And this thing over here is a vector times x. So I'm going to group this thing here, everything that comes before the x, I'm going to call that W1 with a bar over it. That's a vector in Rn. And so what's happening is I'm taking this vector here and I'm doing the dot product with x essentially. Okay? And so we're just going to rewrite this entire thing here, which is kind of messy. We're just going to rewrite this as W1 transpose times x. Okay, so actually I guess here what I'm really calling W here, this is really going to be W transpose, W1 transpose, okay? So this entire alpha expression here, under some simplifying assumptions, we can actually just write it completely, we can actually just write it completely as, instead of involving all the probability density functions, etc., we can write it completely as W1 transpose times x plus W0, where W1 is some vector in Rn and W0 is some scalar. Okay? And so alpha of x is just this expression here. And it's just a nice linear function. All right? And so sort of summarizing that long, terrible calculation, which probably, I mean, I don't know. I don't know if it would have been any more interesting in class, but it's kind of, I think it's instructive to sort of see where this stuff comes from. it all seems kind of magical until you actually see how it works, and then you kind of know how the sausage is made. But essentially what we've shown here is we've shown that the conditional probability of a vector x being in class C1 is just given by sigma of W1 transpose times x plus W naught for some x1 transpose in R, or sorry, some W1 transpose in Rn and W naught in R. Okay? And so the whole idea behind logistic regression is once we know sort of what this functional form looks like, we're not actually even going to bother worrying about what the conditional probability of C1 is, or sorry, like what the conditional probability of this one is, or what this conditional probability is, or what these prior probabilities are. We're not going to worry about any of that, or even learning the parameters that go along with those distributions separately. We're just going to worry about finding what W1 and W0 are. Okay, and if we can do that, then we've successfully modeled the probability that we want. Okay, so yeah, so we really, instead of worrying about all this probability theory nonsense, we're just going to say, hey, all I have to do is find sort of the W1 and the W0 that match, that fit the data the best, and we're just going to learn those two parameters, which is a lot easier because now we're only, this is an n-dimensional vector, so there's n parameters. This is a scalar, so there's n, n plus 1 parameters in total, whereas before we had to learn some quadratic number of parameters if we wanted to sort of model the probability functions directly. So we've really sort of simplified the situation because now all we need to find is this vector and this scalar. Okay, so that makes things a lot nicer. Now, it's kind of a little bit of a pain to have to write down like W1 x W0 all the time. So what we're going to do is we're just going to change the notation slightly, just to make our lives a little bit easier. And what we're going to do is we're going to just sort of like build everything together. So we're going to say, okay, if my x vector is like x1, x2, up to xn, I'm going to kind of write down a change of coordinates where z is essentially z is just the vector that I get by taking a 1 and putting it in front of the x's. Okay, so my original set of coordinates was in Rn. Okay, now I'm essentially getting a set of coordinates in Rn plus 1. And the way that I'm getting these vectors is I'm just taking the original vector and I'm putting a 1 in front of it. So for example, xi is xi1, xi2, all the way up to xin. That's going to give me a vector zi, which is just 1, xi1, xi2, all the way up to xin. Okay, and the reason we want to do that is because then I'm just going to create a single vector w, which is really just like my w naught, then my w1 vector transposed. Okay, so it's essentially I'm just, I'm grouping my vector. Maybe let me write it like this as a column vector. I'm grouping sort of w naught and then w1 together as a single column vector in Rn. And then instead of writing w1 transpose times x plus w naught, that's the same thing as saying just w transpose times z. Okay, so all I did is I sort of add the 1 here so that when I do the dot product with w, the w naught and the 1 are going to hit each other, and that gives me this term. and then the W1 is going to hit X just like it did before, and that's going to give you this term. But I've really just bundled up this whole thing into a single dot product, which just makes our lives notationally will be a lot better. Okay? So, with that in mind, what we really have is we're essentially looking at this. We want the probability, conditional probability here. We've just said that this is equal to sigma of W1 transpose X plus W naught. But that's just the same thing as sigma of W transpose times Z, which, you know, we can also just think of this as the probability of the class Z living in, or sorry, of the vector Z living in C1. Okay. All right. So now, if we want to now essentially find this vector here, this W vector that we're looking for. Now, in order to find it, we need to know sort of what we're trying to minimize or what we're trying to maximize. Okay? And so, what is our loss function going to be? Well, to write out sort of the correct loss function, we can again sort of think of it in terms of maximum likelihood, and so let's set the vector t. This is the vector that's just going to have all the labels in it. So t1, t2, all the way up to t sub m, where we have m points. This is the vector of labels for the points x1 up to xm. Okay, so again, you know, if xi lives in class C1, then t sub I is equal to 1, and if xi is in class C2, then t sub I is equal to 0. Okay. Well, if that's the case, then we can think of this in terms of sort of a likelihood function. So the probability, so imagine we sort of have our data, okay? We have our data, and I want to ask, okay, given these x vectors in my data set, or I guess my z vectors, we're using the coordinate z now, given my z vectors, what's the probability that the labels that come with those z vectors are given by a particular vector t? So say I fix a bunch of, you know, zeros and ones here. If that's sort of the, you know, if this is the vector that I get that's attached to my data, these are all the labels of my data, well, what's the likelihood that I get those labels if my parameter vector is w? Okay? So what we want to do is we want to pick the value of w that makes this the greatest, because these t labels are given to us. So we sort of want to pick the model where the probability of getting the vectors we have is as high as possible. Okay? Or the probability of getting the labels that we actually see is sort of as high as great as possible. So, well, this is just going to be the product of from 1 to n of the probability that label ti is equal to 1 to the power of ti times the probability that ti is equal to 0, given our parameter vector w, to the power of 1 minus ti. Okay? So again, if the correct label is equal to 1, then ti is equal to 1, and this term here is just this probability here, whereas this term is going to vanish because the exponent is 0, so this term is just going to be equal to 1, and all we're really left with for that particular point is this probability term here. On the other hand, if ti is equal to 0, then this exponent is 0 here, and this exponent is 1, and so all we're left with is this term here. And so if the correct label is 0, then the likelihood of that happening is just this thing here. Whereas if the correct label is 1, then the likelihood of that happening is just this thing here. Okay? So for each vector, right, we're taking the product over from I equals 1 to m, which is sort of the number of vectors we have. For each vector, exactly one of these terms is equal to 1, and the term that isn't equal to 1 is exactly the likelihood of getting that label given the parameter vectors w that we have. Okay? So let's expand this out a bit. This is equal to the probability of class C1 given w to the power of ti times 1 minus the probability of class C1 times w to the power of 1 minus ti. All right? Right, the probability of a label being equal to 1 is, or sorry, the probability of a label being equal to 0 is exactly 1 minus the probability of it equaling 1. So therefore we get this expression here. But remember, those probabilities there are modeled by the sigmoid function. So this is sigma of w times zi to the power of ti times 1 minus sigma w zi to the power of 1 minus ti. Okay, and because we don't want to keep writing sigma w zi, so that should be a transpose there and a transpose there. So because we don't want to keep writing that out, I'm just going to call those things y. I'm going to call this yi to the ti 1 minus yi to the 1 minus ti, where yi is equal to sigma w transpose times zi. Okay? So essentially think of it, if we've selected a correct, if we selected a good parameter vector w, then it should give us a high probability of, or a high likelihood of the vector t, which are the labels that we actually see in our data set. That vector should be sort of highly probable given the choice of w. So in essence, we want to make this likelihood function as large as possible by selecting w in such a way that it sort of makes the observations we've seen sort of as highly probable as possible. Okay, so we want to find the parameter vector that maximizes this, but instead of maximizing this, oftentimes what we do is instead of maximizing something, we decide that we're going to minimize the negative logarithm of it. So instead of maximizing this thing here, which we've just been talking about, we'll minimize its negative log. Okay, and so we're going to call that negative logarithm, we'll call it e of w. So it's negative log of this thing we've been working with. And when we take the negative logarithm of that, it becomes a sum from I equals 1 to m of ti times the natural log of yi plus 1 minus ti times the natural log of 1 minus yi. Okay? And this is called, let's get a different color. This is called the cross entropy loss function. Okay? So if we can find a vector W that minimizes this, then essentially what we've done is we've found the vector W that maximizes the likelihood of our observations having occurred. Okay, so this is going to be the loss function that we're going to try and minimize. Fortunately, we're going to see on a homework question that it is in fact strictly convex, and so therefore it has a unique minimum. But let's plan to stop there. I think I've gone on long enough. In class on Monday, I will have these notes kind of on the overhead projector, and we can kind of skim through them quickly to just make sure that we haven't, since you haven't had the chance to ask questions, I'll give you a chance to ask any questions you want on Monday. So in any case, we'll pick this up on Monday, and if you have questions, we will have time to answer them in class on Monday.